Now, coming up next, our first keynote of today on selected topics for 6G enabling technologies that will look into perspectives of the emerging wireless technologies and discuss the open problems, the R&D roadmap associated with these enabling technologies. And to tell us more about all of this, I would like to introduce our first keynote speaker for today. He is an IEEE Fellow, a Huawei Fellow, and an industry-recognized leader in the invention of advanced wireless technologies. He was the recipient of the IEEE Communication Society Industry Innovation Award in 2014 and the IEEE Communication Society Distinguished Industry Leader Award for pioneering technical contributions and leadership in the mobile communications industry and innovation in 5G mobile communications technology in 2018. Wow. He's also a recipient of the R.A. Fessenden Award, or should I say the R.A. Fessenden Medal, rather. Ladies and gentlemen, let's welcome the Chief Technology Officer, Wireless Network, Huawei Technologies Co. Limited, Dr. Wen Tong.
Hello, everyone. I'm very pleased to have this opportunity to participate in international workshop on future communications. I like to talk about the future, and I'm in particular excited to see the vibrant and young Singapore University of Technology and Design is a rising star of our community. Thank you for the invitation. Looking forward to working together with you. In my talk, I would like to share my views on 10 enabling technologies which have the potential to be mature as a mainstream in communication areas. My intent is not to make a precision prediction, but to stimulate our thinking. Some of the discussions are over-optimistic. However, let's follow the proclamation from Alan Key. The best prediction of the future is to invent future. For the past 40 years, wireless communication had a phenomenal success. Mobile technology became a dominant driver not only for communications, but impact every aspect of our daily life and work. Wireless revolution has fulfilled the mission to connect everyone in the world. And with 5G, we are entering into a new stage for connected everything. Communication infrastructure is a platform for the digital transformation of every business. With the rise of AI, in next 10 years, we are very well in a position to create connected intelligence future. And this will be realized by 6G wireless. Before we dive into the discussion of future wireless technologies, let us look at the top transformative technologies that can emerge in the next decade and has the potential to change the landscape of wireless communications. In my view, with next 5 years, there will be some continuous breakthrough in deep learning technologies. The machine learning will be full steam to drive the massive innovation in both hardware and software. It will certainly have a huge impact on communication technologies and services. The next is the innovation. The next is the fast innovation in low Earth orbit satellite communications. It will realize the full Earth coverage of connectivity and shape the future of mobile technology. And it will be a reality in next 5 to 10 years. The third is quantum technology, both for computing and communication. quantum computer and quantum network will have a long-term impact to revolutionize the internet as we know today. In this talk, I would like to articulate 10 technologies in the communication area. To pick these selected topics, we'll try to balance the academia research interest and industry practical challenges. And of course, from my point of view, they have a large impact to design of the 6G wireless. Certainly, I will have the risk of ignorance of some of the innovation from the research community. And these topics are cognition for communication, semantic communications, mobile network for sensing, extreme side link, VLEO constellations, quantum networking, MIMO topics, physical security, in-network computing, and green communications. The first topic is the brain cognition-based future communication, especially for wireless communication. The ambition for this research is to look into the aspect of communication based on the information bit is not the only game for communication. With the success of a deep learning technology, we can revisit our quest in the communication of a human brain-like intelligence. To discuss the artificial intelligence for the future communication, the first question is what is the scope and the capability for artificial intelligence? Here we would like to apply some of the theories of human minds. In particular, we find Daniel Kahneman's work on the analysis of cognition of a brain is useful. The key result of this work is the study of both automatic and the more rational thought process of a human brain. We can tackle the artificial intelligence research by exploring the concept of two systems of the brain. By identifying the function for two systems in our brain, we can understand where is the boundary for AI research we should focus in the near future. In Kahneman's theory, human brain consists of two systems. System 1 is a small portion of a human brain called limbic. This part is formed from 400 million years of evolution. Kahneman identified human intelligence associated with System 1 with the following 6 key properties: fast, automatic, associative, unconscious, impulsive, emotional. System 1 is accountable for 90% of intelligence of our brain, while System 2 is a very large portion of the brain called neocortex. This part is formed from 4 million years evolution. Kahneman identified human intelligence associated with System 2 with the following 6 different key properties: slow, logical processing, analytical, conscious, reflective, deliberative, rational. In a simple term, system is a higher and sophisticated human intelligence, and our current research on artificial intelligence is not yet fully capable to handle these complicated human cognition process. On the other hand, the recent progress of AI can be successful in terms of performing the System 1 functions. The concept of a new model is shown in this chart. Here, we model the 2 users and each with 2 systems, namely System 1 and System 2. The communication and their deficiency between System 1 and 2 are the core part of a theory of a Kahneman study, i.e. the link between S12 and S11. for user 1, and S22 and S21 for user 2. Our interest is to study the communication between user 1 and user 2 at the system 1 level, and i.e. the link of S11 and S12. And perhaps the most interesting part is the communication at the system 2 level, that is the link of S21 and S22. The key assumption for this model is that the deep learning technology can model system 1 very well after a very long training of an individual for user 1 and user 2 separately. We can make such a model for system 1 as a replica or local digital twin available for the other party. In this way, we can deal with the communication instantaneous interaction between system 1 and system 2, between user 1 and user 2 locally, and avoid use of communication networks. In this way, communication between the two users can be reduced much more slower process, in the true sense of the system 2 communications. This is a real sense semantic communication, or even in the effectiveness communication. Semantic communication has been put aside for the communication research for more than 60 years because of the huge success of Shannon's information bit-based communication framework. Shannon deliberately avoided semantic in all his communication technology framework in order to focus the efficient and reliable information transmission. However, with the progress of the deep learning technology, we can re-examine the feasibility of semantic communications. In this chart, I would like to propose a new machine learning communication model based on the theory of System 1 and System 2 framework. In his joint work with Shannon in 1949, Warren Weaver categorized 3 levels of communication models. The first is a technical level, which is the Shannon information theory. The second is a semantic level. The third is effectiveness level. Since fundamentally communication of intelligence is a learning process as well, the two or multiple communication parties can use deep learning to learn communication context in a specific use case and scenarios. Therefore, it is possible to build up semantics and even grammar for the text context after sufficient learning and training. The deep learning model can handle the meaning over the communication at the semantic level or even at the effectiveness level to compress the actual transmission data without loss of intelligence. To elaborate further, the new machine learning-based communication paradigm consists of 3 parts. The first part is a Shannon inner communication channel. The second is the local communication between System 1 models. In other words, interdigital twin communication. The third part is the System 2 communication, and it is a so-called semantic level, which is in fact the semantic outer channel communication. The model has several new properties. It is a low throughput and low latency because deep learning neural network contains a huge amount of memory. After training, the memory captures the self long-term information and the other party's long-term information. To explore the context of memory, we can effectively remove the redundancy of the communication, which the entropy-based method cannot do. One of the most potential breakthrough for the machine learning-based communication is the robustness nature against the channel outage. This is because fundamentally, with this model, System 1 is always on in the cyber world, and System 2 can be on and off. When a mobility user is out of a coverage area, the perceived communication cost still carries on. The interaction among the System 1 are not interrupted, even we lost the communication channel. If we have success in this deep learning-based communication model, it will be a really breakthrough for 6G. The radio wave by nature has a rich property in terms of refraction and scattering. But for the communication purpose, these are not very useful for information transmission. However, the future communication system will not simply just for connectivity, but also for the can be expanded into sensing. In particular, the combined sensing and communication will be critical for massive data needed for the deep learning-based AI. Sensing by using wireless network is a game changer for 6G. We can natively integrate sensing signal into radio transmission wave for every 6G base station, every 6G device. The radio transmission at a wider channel and smaller wavelengths can provide much higher resolution for the real-time environment of the entire network. Even so, at device side, we can use the terahertz technology to scan and retrieve the material detection imaging for many new applications. Therefore, 6G is a network of sensors. It is a cross-sourcing and federated sensing from billions of devices. Furthermore, we can use device-assisted network and network-assisted device sensing to overcome the obstacle such as non-side of sensing. As shown on the right side of the chart, the cooperative sensing and communication will allow 6G network to see almost everywhere anywhere in the environment. The device can send the sensing information to the network so that the network can synthesize the sensing result even for side of a case. Of course, the additional sensing information will be able to utilize to assist to enhance the communication performance. It is very effective in the case of a millimeter wave communication for the beam processing and management with more sensing assisted side information. This can reduce even or eliminate the beam search scanning overhead to reduce the power consumption and extend the battery life. Here, in this chart, we have two examples. On the left-hand side, the UE is in the blocking shadow and cannot communicate with base station. In this case, UE will trigger the side link information to set up a data link path where other links such as D2D side link or, for example, a pad as a reconfigurable intelligent surface. On the right-hand side, the sensing of the people and the car can assist autonomous driving to avoid the blind spot for both for autonomous car and the blind spot for the people as well. Device-to-device communication is a very old topic, but so far it has no commercial success. There are a couple of factors, such as the data rate is not very high compared to the network access. It drains battery power and without any other benefit. and the security is a showstopper. For the future communication systems, several new opportunities can enable D2D communication. For example, the V2X require extremely high-speed side link. Virtual reality and hologram communication require a short-range wireless connectivity, and the emerging terahertz communication can deliver these capabilities. This is a human-centric D2D connectivity picture. It is based on the millimeter wave or sub-terahertz short-range technologies. Because of the availability of a large bandwidth, the link data is at a range of 1 gigabits per second to 100 gigabits per second to enable those XR type of applications. On the other hand, the low power consumption target is very challenging. The design is heavily focused on the energy efficiency rather than the spectrum efficiency. In this case, things like 1-bit analog to digital conversions, signal waveform, and extremely low power FEC decoder will be required to achieve 0.1 milliwatts to less than 100 milliwatts target. In addition, the beam searching and beam management will have to be much more efficient. The transmission and the user data rate, transmission range and the user data rate is plotted with different semiconductor technology implementations. We can see among 4 different mature technology, namely the CMOS, the SiGe, BiCMOS, 3.5, and photonic transmitter. We can see the current status of a sub-terahertz implementation is around 100 gigabits per second and tens of to hundreds of meters of range. Among these, CMOS is out of scope, and the 3.5 technology is promising and worth a good investment for the to further optimize the performance. As a major use case for extreme side link, here is the current autonomous car uploading data rate requirement. The huge amount of sensing data is required to upload to the RSU, i.e. the roadside unit for cloud to perform the autonomous driving processing. These sensing data include LiDAR for 560 megabits per second, camera 320 megabits per second, radar 0.8 megabits per second, and GPS. The total amount of data for every day is at 4 terabytes. And in 6G, the more advanced autonomous driving car will require to upload tens and more time updated data rate in real time. Short-range sub-terahertz transmission is a promising technology for many other industry applications as well. Space communication is always fascinating. It is always challenging for challenges the communication technology to the next level. As I mentioned before, recent breakthrough is the possibility of a massive low-orbit satellite network. Coincidentally, as Tom Stone, the space pioneer and architect Werner von Braun, it was inscripted only one word from the Bible, Psalm 19.1, which implies the sky above proclaims God's handwork. Fully integration of all these network elements in terms of a satellite constellation for 6G architecture design is our object. It's one of our goal. Our vision is that these elements will not form several separate network and independent network. They should be designed as a single network at day one, which means for the radio capability of the network element heterogeneous, but the network is unified in the air interface and mobility management. So we can leverage the global ecosystem and achieve the economical scale. Up to date, the uplink budget is still the bottleneck of non-terrestrial network. There are several new and interesting capabilities enabled by the very low Earth orbit satellite constellation. First, on the left-hand side of the chart, we can see the cloud edge computing can transmit to the band-pipe satellite and to bounce the signal directly to the car. The autonomous driving can be controlled and operated by the edge cloud, where there is no cellular coverage. Another scenario is the smart grid, where low latency service can be applied to the bandpipe satellite to broadcast control command to all the stations and the smart grid with a minimal delay. Second, the VLEO satellite constellation can deliver minimal latency service in intercontinental communication scenarios. It is faster even than the dedicated fiber because the speed of optical transmission is about 70% of a free space light speed. The third is the integrated terrestrial and non-terrestrial satellite. The mobile device can use the dual connectivity mode to avoid the coverage holes. This is a chart I used for the GlobalCom in 2018. In this chart, I did a quick analysis of the capability of a VLEO constellation. This was before the SpaceX announced the Starlink. Now it is almost become a reality. The key disruption is the reusable rocket will dramatically bring the cost of a satellite constellation down. I'm very confident that in 5 to 10 years, this type of a non-terrestrial network will be economically viable. The quantum technology will play a big role in future communication. The foundation is the Bell inequality to that Bell that prove the long distance entanglement of the qubits. It is not difficult to understand. With the quantum entanglement, we can re-examine the encryption and the network routing. One of the challenges for the quantum key distribution is the limited to 2 users so far. To generalize to use many users case for networking purpose, if we use the multiple qubits entanglement, it remains an open problem and a huge technical challenge. Here we present our work in this topic. Essentially, we use a pair qubit entanglement technique in combination with a BB84 protocol to generalize to many users. We consider this result is a breakthrough. For the routing, we can use the concept of entanglement pair qubits chaining techniques as shown in this chart. It is also called quantum repeater. It is basically applied quantum measurement between the 2 pair and chain them together. with the flexibility or even programmable of the quantum measurement, we can program the routing and set up the data path. Since the end-to-end is entangled, the information can route from point A to point B. In my opinion, MIMO is an excessive studied area for communication community. It is also a hugely successful technology, although we still have many engineering and optimization challenges. What is more desirable is the new technology for MIMO. Some of the new proposals are still questionable for their practicality and to be widely adopted by industry. I would like to share my view on the MIMO aspect. From the industry point of view, the MIMO technology can be categorized into 4 parts. The first part is classical MIMO. The 4G LTE standards capture almost all the research results for MIMO. Here, every smartphone is implemented with 10 MIMO modes. However, these designs are not scalable to the higher frequency bands above 2.6 GHz. For 5G, we developed a massive MIMO technology for 2.6 GHz to 5 GHz bands, and the hybrid beam forming for above 26 GHz millimeter wave bands. As we can see, MIMO technology is heavily dependent on the channel propagation characteristic. The next technical problem is to study the solution for the bands above 5 GHz and below 15 GHz, where the MIMO channel property shows a strong Rayleigh characteristics, with a typical, for example, 16 antenna on the smartphone factor. Here, there are a lot of work need to be done. The reconfigurable intelligent surface is now a hot topic for the research community. It generates a lot of enthusiasm. The proposed merit of the RIS are around passive surface with no active radiation, steerable reflection to improve the coverage, large surface to achieve higher gain, the intelligent steering to control the interference, high capacity gain with low cost surface. In the reality, it is not the same as Archimedes' mirror. There are several key practical issues need to address. For example, the need to control subsystem and fix the backhaul near the G node B to gain the strong reflection power, site selection and installation as a base station. The fast and dynamic control surface could be difficult. The site acquisition and additional O&M elements will make it complicated. I would like to plead academia researchers to look into those aspects. In 1943, Shannon proved that for Verdun one-time pad key scheme, once both data rate and key update rate approach the Shannon channel limit, such communication is a secure one. For 6G, we can realize this by introducing full duplex radio communication by using the random channel as a security key. On the left-hand side chart, it shows the one-time pad key scheme concept that is basically is a symmetrical encryption. The secret key is operated at the same data rate as the information rate. It has two problems in reality. First, we will have to reserve half of the channel capacity for a secret key transmission. The second is the symmetrical key delivery has a high risk to be intercepted. The solution will have to address how to generate the symmetrical key delivery mechanics. Our proposal to the solution is to retrieve the random channel with a full duplex radio such that with the same channel reciprocal property and both the encryption and decryption end part, we can apply identical random channel to achieve one-time pad key security. We have successfully conducted a real-world field trial for full duplex radio, as shown in this chart. The multiple UE is in the same sector can be allocated to run full duplex transmission. Furthermore, we also show achieved the so-called bandwidth part full duplex. In other words, it is a hybrid full duplex and TDD FDD in the same frequency bands. And the full duplex subband can be flexibly assigned. The number 9 topic is the in-network computing. The convergence of communication and computing will generate new research topics to look at how to integrate distributed computing with the communication networks. In particular, for the efficient AI service, how to split the computing of an AI model at different parts across the network, how to architect the neuron center and the neural with the pools of computing resources, how to orchestrate the neural resources. In 6G, we will have a huge amount of data with several magnitude or the larger compared to today. These massive data sets are just used for deep learning and generate the AI model purpose. We don't need to transfer this type of data set around the world and share. We have to make this data set to comply the local regulatory requirement as well, such as GDPR in Europe. The AI model is more important than data. The data can kept at the local, the model can be exchanged over the networks. And this requires in-network deep learning, in-network computing as a fundamental requirement for 6G. The distributed learning and distributed inferencing will be the dominant computing for the future wireless communication network. To support the low latency inferencing with distributed computing, it is always desirable to compute a small model at the device or network edge to achieve low latency with less computing effort. However, in many cases, we have to make a trade-off for computing of a huge model to achieve good performance. The inferencing computing with small model and medium model and a large model is not a trivial task. The partition of the model is also associated with the model training and the model creation process. In this chart, we give an interesting example for that is the early termination. In the decision exam that the fully connected layer for convolutional neural networks, if the confidence of early termination is not high enough, then we need to perform the inference computing at next level. In this case, the previous level of computing result is not wasted, and we can use the weight sum of loss function to assist the next level decision. One of the most recent work on the network coding for the inferencing is very interesting. Since the neural network is nonlinear function, The linear code for multiple inferencing input vector cannot be easily reused for linear network coding concept. However, by using additional smaller neural networks as an encoder and the decoder as well, we can achieve the a network coding effect, meaning even some of the inference computing is failed or encountered a large delay, we can still successfully decode the inferencing result. The number 10 topic is a green communication. Green and sustainable development are the core requirement for network and terminal design for 6G, which is a 6G time window. It is also the time window for controlling the global warming. By introducing green design concepts, 6G should aim to improve the overall energy efficiency by 100 times across the network, while also ensuring optimal service performance and experience. As the core infrastructure for digital economic, 6G will make a unique contribution to the sustainable development for humankind. Two big drivers for energy efficiency for 6G. The first is deep learning computing demand is doubling every 3 months, and the open source software has difficult to sustain. The second is low latency for millimeter wave RF amplifier. The single digit efficiency of a power amplifier is and yet to overcome additional 20 dB propagation path loss. These two are long-term research problem for the research community and to look for the new solution and disruptive innovation. To summarize, we talked about 10 enabling technologies, and they are critical for the development of 6G wireless system. We are excited that the research community can look into these challenges areas and make breakthrough. With that, I conclude my talk. Thank you very much.
Thank you, Dr. Wen Tong, for that very interesting presentation on 6G enabling technologies. And now we will move on to the question and answer segment. Now, Dr. Wen Tong, we've got a couple of questions from our audience right now. The first question that we have for you is this. What is the difference between cognitive and semantic networks? Don't they refer to AI-based network intelligence? What is your answer or your thoughts to that?
Yeah, sorry, can you hear me?
Yes, we can hear you loud and clear.
Okay, yeah, so this is a question need a further discussion because the AI today is a very generalized term. So it means a lot of things to a lot of people. But when we come down to the communication, and the specific AI that is implementable from industry point of view, which is deep learning. So deep learning is not, so far cannot cover all the AI aspect or humanity, the human cognition as well. So for example, the AI as of today, they don't have a causality, meaning that they cannot reasoning. So the thing like this is for the communication, especially we go to what is the meaning or intelligence level of communication, is a semantic level. So we need to put some kind of a scope in order to proceed a right architecture at this time frame, let's say 10, 20 years. So in that case, system 1, system 2 is a better way to clarify what is can handle by machine learning and what is yet not can handle by machine learning, and that portion need a communication. So I guess that's what I'm trying to say here.
Thank you, Dr. Tong, for that answer. And I hope that managed to address the question, that question from our audience. We have another question for you, and this is, when we are speaking about modern development and changes of communications and communication systems, according to your opinion, how will new forms and technologies of communication influence interface and relations between people? What do you think?
Oh, yes. So this is a very good question. The interface, the human to human interface, human to machine interface, let's say not machine to machine interface. This is a very big step as every step we go for the communication. For example, the success of an iPhone is the interface with a touch of the screen. So in that case, make many things possible and more convenient than the interface we have before with a feature phone or even desktop, desktop phone. So ultimately, you want to have an interface. First of all, can understand your emotion, your gesture, let's say that level. I think that will be feasible in the next five to 10 years if somebody need. This is our engineering innovation and optimization that we need to do that. And then second, further down the level, that the interface that you can understand the meaning of your communication parties in order to do that. That is neither. This is the part of my discussion of the AI. That means you have a memory, you have some familiarity of your party. So before you communicate, you already have understand quite a bit, either semantic context or that kind of thing.
Thank you so much, Dr. Tong. That was a really comprehensive response to that question. I'm sure our audience members are truly enjoying all of this. We have one more question. Is there time? Yes, there is. Great. Now, this next question, Dr. Tong, is this. Is extreme side link similar to the concept of integrated access backhaul? What do you think?
Some of them, yes. That is a portion of this sort of excessive side link. The distinction is backhaul is long distance. Typically, the side link is short distance, 10 meters or let's say 50 meters longer, not longer than that. The second one is backhaul typically are fixed. That means point A and point B is for long time is a fixed connection, but side link is a very dynamic because you move, environment change, you are entering different room and with different people, etc. So that the dynamic part is very different than the backhaul.
Thank you so much, Dr. Tong. And of course, that answered the question on side link and backhaul. We have another question. I got to say, we have lots of questions from the audience. And this is another one. Due to the unique benefits of in-network computing, does it make sense to see more of its applications in mobile edge computing? What are your thoughts on this?
Yeah. So where to compute is typically depending on the application, especially on the latency. Yes, mobile edge is one of them. That is from technology point of view. But now we have the governance of the data. That means the regulatory will control the data. That means the data may not go to certain country or certain region because of privacy and because the ownership of the data. So that's where the trends need to break down the computing into different portion and yet to respect those regulatory aspects. And as well, there will be some recent good research show up that Federated learning, that means the learning not shipped into one, let's say, Google gigantic data center to compute AI, rather than spread a lot of places. That is a green approach, meaning that total consumption of the power and the energy and the carbon emission, reduce the carbon emission, these are good. So there are other factors as well indicate the trends that need, the in-network computing, in, let's say, general, that term will be beneficial.
Thank you so much for that answer. And we still have 10 more minutes, and I got to see the questions are just getting longer and longer. Lots of questions for Dr. Tong. Everybody's taking advantage of this time. Here's the next question for you, Dr. Tong, and it's this. Can you comment on efficacy and urge of fog-enabled vehicular edge computing, especially in context of collaborative autonomous vehicles or CAV? Your comments on this, please.
Yeah, so these are the terminology aspect. For example, is it a fog? Is it the egg or age, or that? But in the essence, this especially for the vehicular thing, is a distributed. Maybe they have a temporary anchor, but it's fundamentally is a distributed, and it's very dynamic or ad hoc in nature. But they do that way because there are many for the autonomous driving need, and for the communication need, because the sensing require them to do this, or they might be the technology to overcome none of the side communication when you do not have a network. That way will help you. Yeah, so the answer is yes.
Thank you so much. Still have some more questions. The next question for you, Dr. Tong, is this. How high is the reliability bent pipe supported by NTN?
The reliability for that, this is a question that we need a really field test. So far, it looks pretty good because of there are a good way. For example, the low orbit satellite fly very fast, and when you do this band pipe thing, successful acquisition, and compensation, all the mobilities aspect seems feasible. Okay, so we have some trials that's very successful, but hopefully it will be reliable as well, because these are the 2 millisecond latency up and one down and up, so that you can basically send your command to anywhere on the coverage area. For example, the radius as 500 kilometers. It's very more reliable than the cellular network, because there may be somewhere they don't have cellular coverage or network coverage, but satellite covers.
Thank you so much, Dr. Tong. Still have a couple more questions. Next one is this, a follow-up from the last one. It's, will connectivity to NTN now consume more power in UEs? What do you think?
Yes, could be, because the UE power is a limitation for the speed in terms of uplink. If you want to direct connect to satellite, that is desirable. Basically, that is a revolution. So far, this is a unsolved problem.
Our next question is about Huawei's involvement in the VLEO revolution, and it's this. How active is Huawei's involvement in the VLEO revolution? Dr. Tong, can you elaborate?
Yeah. So we do research, and we need there is a we do research. We're sort of support and promote this type of research, because this is a technology, a very promising one. But I think at this stage, it is not yet on a commercial, viable level. The economic, as I said in the presentation, the economic feasibility is remains a question. But there's for example, SpaceX is very successful in terms of
Wonderful. Do we have one last question? Is this the last one? All right. Oh, there's still some more. Great. Fantastic. I got to say, this is a real treat for our audiences here. And they have so many questions for you, Dr. Tong, and they're enjoying every second of this. This next question is, what is your opinion about 6G information security, especially under the US-China trade war situation? Very interesting. Dr. Tong, your thoughts?
Yeah, let's take the two parts. One is a geopolitics aspect. The other is a technology aspect. So the information security, the network security, those are for the technology side. It will continue progressing. There will be technology innovation in 6G timeframe. But the key for the technology community is how develop a security technology which is quantum resistant, meaning in the next 20 years, the highly likely the quantum computer will become viable. And then this is a challenge for any security system for any country. So as a technology community, I think we need find a solution to make it feasible in that time frame, so that the technology provide the security.
Thank you so much. Here's another question that really looks into the future, and this is the last question for our session, and it's this. What do you think are the key topics for wireless research in the next 10 to 20 years? What do you see in the future, Dr. Tong?
Oh, yes. I talk about as a big opening. I talk about technology in the balancing of two aspects. One is the industry challenging. They are even theoretically mature, but we have a long way to make a technology work and to make a technology commercialize. This is one set of technology. I hope the academia people can appreciate that. The other is the new communication theory or new communication technology. Yes, I have to say, for the past 20 years, that area is a bit dry. Not as something in the 70s, 80s, and even 60s. There are many theoretical new theories, new concepts created. These days are not, compared to the productivity at that period, that time frame. I think that's where we need. Or I would like to, promote the research and the put more funding on the research to, to do fundamental and generate a fundamental concept and fundamental technology, so everybody can benefit from that.
Thank you so much, Dr. Tong, once again for your exciting presentation on 6G enabling technologies. And I got to tell you, there's still some more questions and we could go on, but we are out of time. But it's been such a treat for our audiences having you right here live, answering so many of their questions. Thank you so much once again, Dr. Tong.